How can we tell if a function is continuous at a given value of x? There's a couple things to look for. One, does the function have a limit at that x value? A limit that's finite and real. And also, does the output of the function actually match that limit? That's what we're looking for here. I'll do it at -2 first for an example. At an x of -2, we see that there's an output for the function at the point, -2, 2 here. And what's interesting about that point is that if we were to trace the curve and imagine traveling through that point, would we have to lift our pencil in order to do so? That's the first test that you can do for continuity. It's an easy, intuitive test to do, so let's try it here. I'll trace the curve, and do I have to lift my pencil as I go through the x of -2? And the answer is no, I don't have to lift my pencil. So that's actually an indicator that the function is continuous at -2. But let's look at some of the ways to show that it is continuous. We need to show that the limit exists and is finite. So first of all, if we approach from the left side, we see that we're headed toward an output of 2. So the limit of f of x as x approaches -2 from the left is 2. And then if we look at the limit as we approach -2 from the right, that's 2 as well. So now we can decide what the overall limit is. The limit as x approaches -2 of f of x is 2. Is it finite? Yes. Now in the description above, they call that value L, the limit of the function at x equals a, and here a is -2. What we have to do next is the critical step. We have to show that the output of the function equals that limit. So is f of -2 defined? Yes, it is, because we do have a solid dot here. And then what is that output? Well, if you look at the height of the curve here at -2, it's a height of 2. So f of -2 is 2. Since the output of the function matches the limit of the function, that's a way to show continuity. So this would be a yes, and this would be a yes. The limit as x approaches -2 of the function equals the value of the function at -2. So f of x is continuous at x equals -2. Now there may be other x values where the function's not continuous. Let's look at x equals 0, for example. At x equals 0, we see that tracing the curve with our pen would be a little more difficult here. Question is, would we have to lift our pen in doing so? Well, let's see. I'll start tracing it from the left. I'm headed down toward a y value of -1, but once I get real close to -1 here, I'm going to have to lift up the pen and move up to the top and then continue my drawing. So that's an indication that it is not continuous at x equals 0. But technically, why is that the case? Well, the limit as x approaches 0 from the left of the 0 is -1. We're headed down toward a -1 on the left side. But the limit as x approaches 0 from the right side, that's headed toward an output of 3. Since they don't match, the limit doesn't exist at x equals 0. And this is a special type of discontinuity called a jump discontinuity. It's where the limit on the left doesn't match the limit on the right, and they are both finite limits. Let's look at one more. At x equals 2. Here, the limit of the function actually does exist. As x approaches 2, on both the left and the right side, we're headed toward a value of 1. But what's the problem here? The output of the function at 2 doesn't equal 1. It equals 3. Since those two don't match, that's an example of a discontinuity. If you were tracing the curve with your pen, you'd have to lift it. You'd have to lift it for just an instant to go to that high value and then come back. So that's a discontinuity. It's called a removable discontinuity, though. The reason it's called removable is that it would be fixable by changing the output of the function to a new value. So right now, f of 2 is 3. But if we had made f of 2 into a 1, then we would have had continuity. Now, of course, the function's value is not 1 at x equals 2. It's actually 3 at x equals 2. But it's technically called removable because it could be fixed if we were to change that output value.